Okay, so last time we were doing Berlekamp, and so we deduced that we want to solve, we want to find a g that such that g raised to p is equal to g mod f. F is the polynomial that is given to you to be factored over a finite field whose characteristic is p. So we observe that the solutions of j raised to p equal to g, they form a fp vector space, and that vector space now we want to find. Okay, every element in the vector space we want, which will be through the basis, through some basis, right? Otherwise the vector space is exponentially large, but basis elements are few. So what we will do is this green part, so Cij are the unknown coefficients, x is for the polynomial f, so it goes from 0 to d minus 1, and y is for the finite field, so it goes from 0 to n minus 1. Okay, so there are dn unknowns. So LHS is xi yj and RHS is xpi ypj, and you want to now compare the monomials both sides. You will get linear constraints in Cij, and then you find Cij by using a linear system solver. Okay, so that part is straightforward. Based on this, let us now write down the formal algorithm. So Berlekamp's algorithm is mainly two steps. So step 1 is compute the vector space through basis elements. So g raised to p is g, and degree of g should be limited. Well, for vector space you also want degree 0. So 0 to d minus 1, so you find all the g's. Yeah, so before going to the next step, let us first analyze the time complexity of this. So what is the dimension of V over Fp? Right, that is at most d times n, because you had dn unknowns. So you will basically, this system will give you a dn cross dn matrix of constants which are just numbers 0 to p minus 1, and essentially that matrix you have to then in a way invert to find solutions of the linear system. So basis of V requires linear algebra algorithms. So what is the time complexity of that? So if you naively do it, then time complexity will just be the same as matrix multiplication, which is dn whole cube, Fp operations, right? So that is dn cube times log p. So this much time. Dn cube Fp operations, so that is that each operation is linear in log p, and then O tilde for the log factors in the fast algorithms. Uh, but even before you apply linear system solver, you had to construct this matrix, right? So the construction of matrix also costs a bit, because you have to compute this x to the pi, y to the pj, and then you have to divide mod f, compute the remainder. So all that also costs something, but it will not be as dominating as this. So this is the dominant term. But just for satisfaction, we can also write down that expression. So that is, so what is that? So you had P around PD and PN, right? So that you can do by, let's say, repeated squaring. So log PD, log PN, and so that many repeated squarings, then you have to multiply them, which will be, well, maybe this is over optimizing. So you, first of all, the number of monomials already is Dn in your polynomial, so you cannot save on that. And so that much space you need, plus what you need is the computing the monomials x to the pi, y to the pj. So that all that can be done in around, I would say, d log pd and log q. So dn is for the number of I comma j, and when once you fix ij, then you have to compute x to the pi, x to the pi, y to the pj. So that is by repeated squaring you can do this in log PD, and then you have to also divide by f. So maybe I collect them together like this. D log q is finally the mod f computation in the finite field. It's log PD times d log q, because you have to compute mod f over in the finite over the finite field. So that d log q will hang around. Is that clear? But whatever it is, it's always smaller than the dominant term. So this will not matter. This is really maximum quadratic, while there you have already paid cubic time or super quadratic time. So that is the cost of computing V, all the way down to bit operations, number of bit operations. Yes.
Should it not be d log PD, because you are computing x to the power pi and y to the power pj?
Yeah, you do it by repeated squaring. Repeated, the number of squarings will only be log PD. Okay, so there is an important point here. The point is that linear algebra is actually, it is truly polynomial time in the input size, because as you can see, there is no factor of p and there is no factor of q, right? So even for very large characteristic p, this is truly polynomial time. Okay, linear algebra is not the bottleneck. So this you can do quite fast, irrespective of what the characteristic is. The problem will happen in the second step. So in the second step, now you have a G. So you pick a G in V. In fact, you can pick it to be a basis element. Pick a basis element G in V, which is non-constant. And what do you do with this? this non-constant polynomial g. How will this factor f? So you basically compute many GCDs with f. You compute this GCD f with g minus I, and call it h. So if this h is a proper factor, is not 1 basically, then it is a proper factor of f because it has degree less than d. If it is non-constant, then it has degree at least 1. So this will be a proper factor of f. So you can output it. Okay, so you will be done. This is a for loop. So you are doing this for all i's, numbers 0 to p minus 1. How do you know that one of them will succeed?
Degree of g is less than.
So
So if none of them succeeds and f divides g minus I, then degree of f should be greater.
yeah, so the key thing is that equation g raised to p is g mod f. So remember that g satisfies that equation. So since it satisfies this box, f divides g raised to p minus g, so f divides some part of f has to divide some g minus I, because g raised to p minus g factors as product of g minus I. So something in f divides some g minus I. When you take GCD, then that part of f comes out as h. F is irreducible, but that you have checked separately. That already in the pre-processing you checked that f is reducible. So the only option is that you will get an output h here. H may not be. No, our problem of factorization is only to find a non-trivial factor. That is how we define the problem. Everything else you can just repeat this subroutine. Okay, so the time taken here is so there is a for loop p times, and each time how much is the GCD cost? GCD is soft linear. So linear means d log q. Okay, so this is the place where p appears. So the sum of step 1 and step 2 is the overall time complexity. And it will make sense only when p is small. If p is exponentially large, then this will be a useless algorithm. But when the characteristic is small, it's a good algorithm. In fact, right now, this is the only algorithm you know to factor. Okay, so what we have proved is this theorem. Any questions about the algorithm? Just 2 simple steps now. So this is Berlekamp's theorem from 67. It's an old theorem. So polynomial factoring is in O tilde p times dn omega time. So omega is the matrix multiplication exponent. Okay, so p times dn omega, is this correct? So in step 1 you can replace the standard linear algebra with methods using fast matrix multiplication. So dn cube will become dn omega. So that sum is bounded by p times dn omega. That is correct because omega is at least 2. So again, second term will not matter. And the third term, so step 2's complexity is also below p times dn omega, right? So that's the final result. So assuming that fp is small, it depends on what is the field extension degree of fq, which is n, and what is the polynomial degree, which is d. So in that it is dn raised to some 2.4, okay, super quadratic, but subcubic. So if p is small, which means dn to some polynomial, then this is polynomial time algorithm. Then this is a deterministic polytime algorithm. To factor polynomials over finite fields. For low characteristic, where low means this, poly in dn. So in many CS applications, this is already good enough. Because in many CS applications, the characteristic is not that large. One works over a large finite field with low characteristic. So in the next lecture, we will see an algorithm which will work also for large characteristic. Right. So in particular, if you have a large prime field, then this algorithm will not help you. So Q is equal to P and P is large. So in that case, you have no algorithm, really, no practical algorithm. I mean, Berlekamp is not practical. So a different idea is needed, which we will see in the next class. But it will not be deterministic. So for large P, we will see a different algorithm. It will be polynomial in log P instead of P. But then it will be randomized. It will be randomized polynomial time algorithm for general polynomial factoring. So do you know what is a randomized algorithm? Anybody here who does not understand the difference between deterministic and randomized? Okay. So randomized is enough or it's okay for practical implementations, but theoretically you want a deterministic algorithm as well. That currently we don't know. So what is open is general polynomial factoring. In deterministic polynomial time. Okay, so this is still an open question. Although in practice, how this is solved we can see already in the next class. But doing it really in deterministic polynomial time is open. Yeah, any questions about Berlekamp? So then we will build a bit on Berlekamp because it gives some interesting tools, okay, which will be helpful also in other places. So let me call it Berlekamp as a reduction. So what it means will be clear later. But we will see Berlekamp as giving two major tools. So first tool will be a polynomial invariant which is called resultant. And second major tool will be that Berlekamp algorithm gives us a way to reduce polynomial factoring from finite fields to prime fields. Okay, with very little cost. So in deterministic polynomial time, it actually reduces given input polynomial to one which is in the prime field, which means that the coefficients are only 0 to p minus 1 for a prime p. And if you can find a factor of this polynomial, then it will give you a factor for the original input polynomial. Okay, this is the meaning of reduction. So Berlekamp algorithm actually gives you these two major tools. So let us discuss these two before we move to the next algorithm. So Berlekamp's algorithm can be used to reduce polynomial factoring over a general finite field Fq to that over Fp. In deterministic polynomial time. So why is this non-trivial? Reducing Fq to Fp is non-trivial because your input polynomial may not have anything to do with Fp. It may have factors which have coefficients from Fq but not Fp. Right? So your input polynomial may start with coefficients in Fq and its factors also may have coefficients only in Fq. So it is not clear what is even the connection with factorization over a prime field. So what Berlekamp does is that it will change your input polynomial to a completely different polynomial, possibly, which will have Fp coefficients and it will have Fp factors as well, if the input polynomial had Fq factors. Okay, so it connects potentially very different problems. Because factorization, you should remember, always depends on the field, right? So Fq and Fp should be seen as totally different fields. These are two different factorization questions. Yeah.
P is the characteristic.
Yeah. P is always the characteristic. P is always a prime.
So this P is related to Q. That Q is just exactly P. It's not any prime. It's the prime.
Doesn't matter. I mean, polynomials over Fq may still be irreducible when seen in Fp and may not even be defined there. So the factorization questions are really different questions, but Berlekamp will connect them. So it will connect by a polynomial invariant which is called resultant. So what is a resultant? Is there anybody here who has seen resultant or resolvent term before? What does it mean? Okay, good. So you will learn something new. Yeah, the term may not suggest anything what is going to come. So suppose you are given two polynomials over some field f. So Euclid's GCD algorithm that analysis gave you this Bezout identity. So UA plus VB is equal to the GCD of them. Right? This was the identity, and there were additional properties, restrictions, that degree of U and V are also limited. So both of them are respectively smaller than degree of B and A. Right? So this was the result of Euclid's GCD algorithm. So you know that U and V exist with this limited degree. Without going through Euclid's GCD algorithm, if you want to find them, given A and B, so you can see this equation as a linear system in U and V. Right? Because if you assume the coefficients of U to be UIs and V to be VJs, then in UI and VJ you have a linear system by comparing the coefficients, both monomials both sides. Assuming you have computed A comma V GCD. Yeah, so that linear system basically corresponds to a matrix, and that matrix has a determinant. So the question is, what is that determinant? Okay, so that determinant we will call resultant. Related to this is a linear system of or in how many unknowns? Yeah, so degree of A plus degree of B, which is degree of the product. So in degree of AB, many unknowns. So let us write that equation. So you have U0 plus U1x to U degree B minus 1 so U times A is this plus you have same thing for V up to degree of A minus 1 times Bx, and the sum is equal to the GCD with respect to x variable. Right, so this is the equation that, or the constraint that U and V have to satisfy. And as you can see, since A is known, B is known, and GCD is known, the UIs and the VIs, they satisfy merely a linear constraint. I mean, they satisfy a sequence of linear constraints. So the way you will extract those constraints is by comparing coefficient of x to the 0 on both sides, then x on both sides, x square on both sides, and so on. Right? So you will get around degree of AB many linear constraints in that many variables. So it's a square matrix. So the question is, what is the determinant of this square matrix? So comparing x monomials on both sides, we get a matrix, let's call it M sub A comma V. It has entries where the entries are all constants, of course. So F entries of degree A times B order. The matrix size is degree AB cross degree AB. And what is the relationship between the entries of the matrix and the coefficients of A and B?
You will be taking degree AB terms.
Sorry, degree.
Where you are taking degree AB terms.
You compare the x monomials, as I said. So what is the relationship between the matrix entries and the coefficients of A and B? Can you see? So the coefficients of A and B will appear in the linear constraint as it is. So they will appear in the matrix as entries. Right? So simply the coefficients of A and B, they become entries of M, obviously in the correct locations. So we will not go into the exact location details, but just make this observation that its entries are coefficients of AB. Or when not applicable, they are just 0. Yeah, so basically the input polynomials given to you were A and B, and look at the coefficient vectors and just place them suitably in a matrix. Okay, that is the matrix M A comma V. And the linear constraint you get is M A comma B times these unknowns U0, U1 and so on, and then V0, V1, so on. So Um times this is equal to a vector of constants whose entries come from the RHS, which is GCD. Again, these are just coefficients. Right, so on the LHS you have a matrix multiplying this vector of unknowns, which is degree AB many. So M is a square matrix, and on the RHS you have a vector of constants, they are coming from the GCD polynomial. Right, that is the linear constraint we were talking about. And finally, resultant is just the determinant. That's the definition. So resultant with respect to x of A and B is defined as the determinant. Yeah, we'll come to that. So this determinant lives where? What is it? It's a constant, so it's in the field. Right, so it is, so you are basically mapping two given polynomials to the field, to a field element. That's what it does. Now, it has a huge number of properties. So one of which will answer your question. But any questions about the definition or the setting? Okay, so what is this good for? So we'll show the first major property of this, which is that if the resultant is non-zero, so remember that the way resultant is defined, given two polynomials, without doing any computation, you can just define the matrix and compute the determinant, which is the resultant. Right, so this is simply this is just one determinant computation, no extra computation required, and you can check whether it is zero or non-zero. So suppose it is non-zero, what can you say about the GCD?
You will get unique U and V.
Yeah, and now unique U and V means what? In Bizu identity, when are U and V unique? So actually they are unique only if GCD is 1. Okay, so that's the so this is an alternative to Euclid's algorithm. Okay, you have a completely different way of deducing something that you deduce by Euclid's GCD, which is that you just take these two polynomials and compute the appropriate determinant, again by linear algebra algorithms. And if the value is non-zero, then you know that the polynomials are co-prime. And if the resultant is 0, then it means that there is a non-trivial GCD. Okay. So this is the basic property, and it's a major property because you can also do this with multivariate polynomials. So instead of one variable, if you had 10 variables in A and B, then you can extract the resultant with respect to x1. So if you extract resultant with respect to x1, what do you get? What remains? The remaining n minus 1 variables, right? So resultant is multivariate, but this property will still hold. So resultant with respect to x1 is non-zero if and only if the GCD with respect to x1 is 1. Okay, so also for multivariate, you can apply the same argument. So it actually gives you relationship between common zeros of AB and the projected zeros. So when can a projected zero between of AB in n minus 1 variables, when can you lift it to n variables? Okay, so those questions actually get related to resultant. So one such question is there in your assignment. So let us first prove this. So recall the equation UA plus VB equal to GCD. Now if the matrix determinant is non-zero, it is equivalent to saying that unknown vector is unique, because matrix inverse exists, right? Since the inverse exists, the unknowns are unique. Well, they exist and they are unique. And so now this uniqueness, what does it say about GCD? Right, that is the question. So claim is that this means that AB are co-prime. Do you agree? Why is that true? So suppose AB were not co-prime, right? Then you can find U times A equal to V times B, or U prime times A equal to V prime times B, where U prime, V prime have their degrees limited. So this you can do just by so for example, what can you take U prime as? Yeah, so you exactly. So you basically want this to be equal to AB, something like that. AB by GCD, I guess. So which is LCM, right? Yeah, AB by GCD, which is also LCM. So you basically want to get to LCM, and there will be a U prime whose degree will be smaller than B. That will give you this, because the GCD is non-constant, right? So U prime is equal to B by G, which is degree less than B, and similarly V prime is E by G, which is degree less than A. So U prime, V prime exist, but clearly they are not unique. Why is that? Actually, I should be careful. We were talking about that equation. So what does it tell you about UA plus VB equal to G? You want to show that U and V are not unique. So do you know how to modify UV to some other solution?
Subtract U prime and
Exactly. So you use U prime for that. Okay. So you another solution is U minus U prime. And here is V plus V prime. Yeah. So the degree is limited. The degree of U prime and V prime is equally limited. So when you do this perturbation, you get a different solution than UA plus VB. So that is the simple property. Okay, so limited degree UV are still not unique. This is what happens. This completely fails when G is 1. Okay, then the limited degree really gives you a unique solution. Well, which you can prove by looking at the determinant. So by the uniqueness of UV, you can deduce that AB have to be co-prime. So that is one direction. What if AB are co-prime? If AB are co-prime, then why does UV exist by the Euclid algorithm? Why are they unique?
unique inverses modulo if we take B.
Yes, so you jump this and go to the to this matrix, and by studying the matrix you can reduce that. So this is all if and only if. Okay, so you basically have two views of Euclid GCD. So one is this Bezout identity view, and the other is the matrix or resultant view, and you can go back and forth. And these two views correspond to actually two different algorithms. One is the GCD algorithm, usual recursive algorithm. Other is the determinant computation algorithm. So everything is, all that is actually contained in this single lemma. Is that clear? Any questions?
Can you explain the only if?
The other side, okay. So suppose that AB are co-prime. So you have UA plus VB equal to 1. Well, I can do it by calculation. It's actually, that's easier. No, let me just do it straight in a straightforward way. So suppose UA 1 is equal to UA plus VB equal to U prime A plus V prime B. So then you take the difference of these equations. So you get U minus U prime A is equal to V prime minus VB. But you have assumed that A and B are co-prime. So this means that, I mean, this leaves you with very few options. It actually means that both U minus U prime and V prime minus V are 0. Okay? Because this A has to then divide V prime minus V. But then by degree, only it can only divide 0. So that's the converse. That is actually simpler than going via matrix.
It's also visible from that equation. AB by G.
So you use this was for the green one is for the forward, and for the converse you use this other calculation. So then that gets connected to the determinant or matrix inverse. Right. So with this understood, now let us move to the other major properties of resultant, which is useful in the case of multivariate polynomials, and also in which is similar to actually elimination theory. In computational algebra and what is called elimination theory. So let me give you a taste of that. So suppose you consider now bivariate A and B. Now bivariate polynomials are extremely different from univariate polynomials. This is a much harder case. For example, here now the roots may have no connection with the degree. In fact, roots can be infinitely many, common roots. That you can think of the integral case. In the integral case, common roots may be infinitely many. So now for these possibly infinitely many roots, you can look at the question of projection. So you project the root to the first coordinate, and you can ask the question of what are the possibilities of the first coordinate. In other words, fixing x1, how many lifts are possible to x2, or is there actually any lift possible to x2? Okay, so those questions you can ask, and they will be answered by resultant. So,
What do you mean by leaf, sir?
so a point where the first coordinate is your favorite fixing. So reverse, I mean fibers of projection, pre-images of projection. So you can consider here resultant with respect to x2 of bivariate AB, which will now be a polynomial in only in x1. Right. So this is why elimination theory. So you are actually eliminating a variable. You are given two equations, so combining them you can eliminate one variable. So now you are in the univariate world, where things are better. So you, in particular, this resultant can only have finitely many roots. Is that true? What if the resultant is 0? It may also be 0, right? So either this is absolutely 0. If not, then x2 has only finitely many possibilities, right? But what do these possibilities entail? So if you take a root of the resultant and fix your x2 to be that, what is the relationship between resultant and roots of the resultant and common roots of A and B? That's the question you can ask. Yeah, so let us give this thing a name, maybe Cx1. So let me make this observation. So C alpha equal to 0 implies that in A and B, if you fix x2 to be alpha, x1, in A and B, if you fix x1 to be alpha, then what? Then these two polynomials have a common root. Do you see this? So suppose not. Suppose these two polynomials don't have a common root, right? But these two are univariate polynomials. So not having a common root could only mean that they are co-prime, right? So you have then this substituted A and plus V times substituted B equal to 1, right?
Resultant is non-zero, then it is co-prime.
No, the lemma was this. Resultant non-zero means, resultant 0 means that there is a common root. So you read this lemma as resultant is 0 if and only if the GCD is non-1, which means that there is a common root, right? So actually resultant, if you kill the resultant, then there is a common root. So from this lemma, just by reading the lemma correctly, you can deduce this property. Okay, this is a direct corollary of that lemma. That a root of this resultant will definitely lift to a common root of original bivariates. Okay, so this is the meaning of lift and elimination. So you are eliminating a variable which is x2, finding a root in x1, and then you know that this can be lifted. So this kind of gives you a way to solve also bivariate polynomials using the univariate machinery, right? So this is actually the starting point of very big theories.
Are you assuming the field is algebraically closed? Otherwise, why should it have a common root? It could just have a common factor.
Yeah. So say it has a common factor. Yeah, you can replace this by factor. If f is not algebraically closed, then you will only get a non-trivial factor. But intuition is really from the roots. Okay, so let me, so resultant with respect to x2, let us continue on that. This has a nice Bezout identity actually. So let me prove this as a lemma, that if the GCD of these AB with respect to x2 is 1, then there is this bivariate Bezout identity, okay, but it will be slightly modified from what you have seen before. So what we'll say now is UA plus VB. Do you know this already? So Bezout identity says that UA plus VB is equal to 1, right? But that was in the univariate case. What will you get in the bivariate case? You will actually get resultant. That's the beauty of it. Where UV are these are polynomials limited degree.
In univariate case, it was hard to describe this because resultant was a number list.
Yeah, it was a field element, non-zero, so invertible.
Yeah. Okay, it's more clear.
So U and V will have limited degree, talking only in terms of x2. Okay, so individual degree of x2 in U and V is limited by whatever you saw before, which is for U it's B and for V it is A. And goes without saying that U and V, we are looking for polynomials. Okay, so in the bivariate case, we seem to be stating a new identity, which is when AB are co-prime with respect to x2 variable. By the way, what is the meaning of this? We should have defined this. What is the meaning of GCD of two bivariates with respect to x2? Sorry?
Push x2 as the coefficient.
No, I would say the opposite. Push x1. Yeah, so what this is saying is that there is no common factor of A and B dependent on x2. Okay. Just like in univariate we say A and B are co-prime if there is no common factor function of x. So here we'll make the same statement that A and B don't have a common factor function of x2. Okay. So maybe this needs a definition, although it's a natural extension of co-primality from univariates. So if you want, let me just say co-prime over fx1, the field. Okay, so it's the same notion of co-primality over a field, but the field here is a function field fx1. And so with that there is only one variable, which is x2. Okay, so we are talking about co-primality over function field now. So it means the intuitively correct thing. So if that is satisfied, then there is a Bezout identity, except that one will be replaced by resultant. The reason is that, or intuitive reason is that this resultant is a polynomial in x1, and co-primality is not able to see these polynomials. So basically any polynomial in x1 is thought to be as equal to 1, right? It's in the function field. So this is a more precise identity than what you got before. So here we are saying that actually if you restrict UV to these degrees, then UA plus VB will be equal to exactly the resultant polynomial, which is free of x2. The proof of this is actually quite straightforward. So we can finish the proof and then wait for the next class. So this is just by So, this Bezout identity over fx1. So, let me say the field is fx1 function field and the variable is just one, which is x2. So, over this, in this, so you will get u prime a plus v prime b equal to 1. Right. So, by what you have seen before, the univariate case, so think of the variable to be only x2 and the field to be fx1. So, in that polynomial ring you will have u prime v prime, giving you u prime a plus v prime b equal to 1. Right. That is just invocation of Euclid GCD, standard Euclid GCD. But the problem is that this u prime v prime have maybe you are dividing by univariates in x1. They are not polynomials, right? So, you want to make u prime a polynomial in x1, x2 in both the variables. So, to do that you have to multiply by the denominator, and that denominator is guaranteed to be a factor of resultant. Why is that? Do you see that?
So can you explain this part once again?
Oh, this part is GCD part. This is just invoking Euclid GCD for univariates. But u prime may not be a polynomial now. They may not be in fx1, x2 because they are by definition only guaranteed to be in fx1 field with the square bracket on x2. So, to make them polynomials you have to multiply by the denominator. So, by clearing away we get uv polynomials and a w which is univariate in x1 such that ua plus vb is equal to w, right. So, on the standard Bezout identity you clear away the denominator. So, denominator can only be a function in x1, a polynomial in x1, so that is w, and so u is just u prime times w. That is what is meant here. Thus making u and v polynomials in bivariate. What is the relationship between this w and resultant? Right, that is the content of the lemma. So, how do you relate these two? This seems to be arbitrary. Why should it be something so special as the resultant? U prime and v prime are actually, you look at the linear system which gives u prime v prime. So, you look at the matrix that gives that to you. So, consider the equation m a b times you have u prime written down here expanded and v prime expanded as vectors, and this is equal to 1. right? So this is the equation that gives you u prime and v prime, the coefficient vectors of u prime and v prime, and this resultant matrix appears here, right? That we saw by the definition of resultant. This will be the equation giving you u prime v prime. What are the entries of this matrix? Coefficients with respect to x2. So this is actually a matrix over its entries are in fx1. So this is a matrix whose entries are actually polynomials. They are univariate polynomials in x1. They are free of x2 in particular, right? And the determinant of this is the resultant with respect to x2. Now can you say something about w? What can you say about the denominator that we cleared? So actually you have to recall what is called Cramer's rule in linear algebra. So when you want to solve this matrix equation, how do you get the solution? By actually here, yeah, here it is simpler. So you simply have to compute m inverse times elementary vector 1 0 0, and that will give you the first entry of m inverse. And what is that? So that's to do with the adjoint of the matrix. Divided by the determinant of this. Okay. So basically, matrix inverse is some matrix divided by the determinant, and that matrix happens to be adjoint. Entries of adjoint are, what are the entries? They are the same as before. So they are again univariate polynomials in x1. So the numerator here is a polynomial in x1. Every entry is a polynomial in x1. Denominator is also a polynomial in x1, but it is the resultant. So you cannot clear anything worse than this. Okay, so w in particular you can take to be resultant. So that is why you get the identity in the lemma. So this means that w can be set to resultant. That's it. Okay.
We can get better than the resultant.
Yeah, but that is out of control. That we cannot say in general. In general, it can be as bad as resultant. So the generic case is resultant. Some specialized cases may give you a factor of resultant, but that is not important. All our results will be based on this identity. Any questions? So we'll discuss more about resultant next time.